Well, thanks to AWS reInvent for having us here. It's really exciting to get a chance to talk with cryptocurrency, about cryptocurrency. So to kick it off, I'd like to ask a question. Who's familiar with cryptocurrency, feels familiar? Yeah, awesome. Now keep your hands up. Keep your hands up. So over the last couple weeks, you can put your hands down if you saw your crypto portfolio decline in price. Yeah. So I started Coinbase 4 years ago, and when I started, the price for a single Bitcoin was $1,300. It pretty quickly declined after that, and it stayed at $200 for the next 2 years. And just this last year, we actually saw the height of the price at $18K. And pretty often, people want to talk to me about the price volatility. It's exciting, it's top of mind, it's what's happening. But the conversations I find much more interesting are with entrepreneurs. What are the products people are building? Beyond speculation, what's happening out there? What are the perspectives from entrepreneurs? And I know that a lot of you in the audience today are entrepreneurs. So I wanted to give us a chance to meet our neighbor, to talk with someone and give them the 1 to 2 sentence perspective. What's your perspective on cryptocurrency, on blockchain, on Bitcoin specifically, whatever you choose. So let's do that for just a minute. Turn to your neighbor, introduce yourself, and give them your quick perspective.
No.
You can sit down if you want.
It's fine. Cool.
But you don't have to.
Yeah.
Awesome. We'll get a chance to wrap that up here. Wrapping it up. All right. So we'll wrap this up, but don't worry, we're going to come back to that at the end. So thanks everybody for taking a chance to share with your neighbor, talk about what this industry means to you. So Jake and I developed this talk based on our personal perspectives. I'm currently the product manager for Coinbase's back-end technical team that connects the Coinbase applications to the blockchain. I've also had a chance to wear many hats at Coinbase, so I led strategic business development. I also helped create our first iteration of incident response in the early days, and was the solo data lead creating our board decks and company metrics in the much earlier days. And Jake also joins me today.
Yeah. Hey, everyone. I'm Loud, and my name's Jake. I'm a senior engineer on this same team that she works on, this crypto payments team. So I get to work on all of our blockchain integrations. Any sorts of sends and receives that you do on Coinbase are going to go through our systems. In my time, I've worked on adding 3 or 4 different new currencies. I've also helped rewrite parts of our hot wallet management system to be more efficient, save money, help out the network. And we've got a lot of cool things coming up in the future.
Yeah, so today we're going to start off in Cryptocurrency 101. Give the 10-minute overview. What's the promise of blockchain? And how have we seen the major themes play out over the last 10 years? From there, Jake's going to take a deep dive on Crypto 201. What are really the technical nitty-gritty of this, and where's the magic happening there? So kicking us off, I want to talk about the promise of blockchain and the reason that I joined Coinbase. The core, the heart of it, is the decentralization. That's the functionality that's incredibly interesting. It's an opportunity for anybody to audit the code, to modify the code, and to execute the code that's controlling their currency, that's running their systems. And that is an incredible opportunity. It's not possible in our current centralized system. So in our current system, individuals need to rely on a single bank, on a single country's governance and code in order to handle their money. There is no opportunity to change between that. So it requires this trust between 2 people. And I think what we've seen is centralization has had some pretty big challenges, specifically around data. So when data's all in one place, obviously hackers are interested in it, so they come and start attacking it. And we've seen Target, Equifax, Chase, it's commonplace for companies to get hacked for their customer data and information. That's very possible in a centralized system. And really thinking about the gravity of this, 143 million people is the population of Russia. That is as though all of Russia lost their credit history. And they don't have any other choice. Decentralized systems are what you need to choose. And this is where decentralization was such an interesting and exciting concept for everyone. Because in this one, it's open source. You can read it, the community can modify the rules, and as an individual, you have control to switch between systems. It's cross-border. And you can decide, it all relies on code. It obviously reduces the middleman, that has practical implications of reduced fees. And that was the exciting part. That was the promise, the crux of this industry is decentralization. Imagine a system where you can audit and where you can change the rules that control your money, that control your financial systems. And if you don't like it, you can leave with almost no switching costs. It's been really exciting to see this idea, this little seed of an idea grow. How do we find opportunities where centralization maybe is outdated, maybe isn't the right choice, and move into decentralized systems? So that brings us to a short history of crypto. It's been fascinating for me to watch because when I started this, we had a grand idea. I see you nodding your head, and that's so exciting because it's true, the promise is big. And we've seen a lot of industries start to adopt it and move from centralized to decentralized. And there's still a long way to go. If you think about the internet, it took 15, 20 years to really have it gain momentum more. Yeah, and so I think we're going to continue to see that, but the best way to look forward is to look back. So taking a chance to look back, in 2008, 10 years ago, is when the Bitcoin white paper first came out. Everyone got excited. Took quite a while to gain traction. Coinbase was founded in 2012 as one of the first major consumer companies in this space. In 2014, merchant payments were the largest initiative. And they were the first main use case of cryptocurrency. And it's a pretty obvious jump, right? So you go from, it's a payment method, it's a currency. Great, now we can accept it as a payment. And we worked with companies like Time, Stripe, Dell to start accepting this. What was fascinating, though, is in the United States, we have really good credit systems. And people used Bitcoin. They used it for novelty, they used it for security, but ultimately defaulted back to their credit cards because you get points. Your incentive system wants you to choose credit cards. And so that makes a lot of sense. There are still thousands of consumers, tens of hundreds of thousands of consumers that accept cryptocurrency today. But they happen to be smaller shops, more international shops, and that's where it found a better niche. So then in 2015, enterprises sort of turned their heads. And they were like, we like this promise you have. We like this idea of anonymized data, of cryptographically secure information. How do we start using this? And we saw a lot of private blockchain initiatives come out of that. Lots of companies getting together, R3 starting initiatives for large enterprises to work together and utilize this technology. Finally, in 2016, traders, investors started to turn their head. And they saw the opportunity in speculation. So how can we utilize this asset as a new asset class, a sort of emerging asset class? Allow ourselves to diversify, to speculate in a whole new realm we hadn't heard of. And from that, we saw a lot of cryptocurrencies come out of it, explode. Lots of people creating new ideas, new opportunities for them. And then 2017, Ethereum really drove smart contracts and decentralized applications. This was exciting because it gave us an opportunity to really move into that decentralized realm. I think we were trying a lot of different things. We saw a lot of interesting use cases that people got involved with. But decentralized application is what happened if you gave people an opportunity to move any of the systems they have now into a decentralized world. What would be created out of that? And that's been where we are now. I won't hit to 2018 because I think this conference will probably show us a lot about where that's going as well. But this is a brief history, and I think you can see that we've found a lot of different use cases, tried a lot of different things, and we're still doing that. It's early days for us, and it's exciting to be on the pioneer of it. And the truth is, the heart of this industry, it's in the technology. And that brings us to cryptocurrency 201.
Yeah, thank you.
There you go.
Cool.
Good.
Cool. So yeah, we're going to get into the technical details now. So in this part of the talk, we're going to get into specifically what is a blockchain, how do they work, what are some of the cryptographic sort of ideas behind it that power it and make it the secure, immutable ledger that it is. And then we're going to compare some of the features that Bitcoin's come up with, that Ethereum's come up with, and just kind of talk about how they work. And then a little bit into sort of the future and what's coming next. This stuff's about 10 years old now. It's 2018. Bitcoin came out in 2008. A lot has happened in that time, and there's a lot more to come. So to get started, we'll talk about what is the blockchain itself. What are these key ideas that came together to make this online payment system in a distributed, sort of decentralized way? And there's three concepts here. We have this first one of these economic incentives. You'll hear this term thrown around like crypto economics, which is this new idea of combining some economic principles with game theory, with blockchains, and it's this idea that you can incentivize people to do the right thing in the network. Because if they do the right thing, they're going to get paid for it, and if they do the wrong thing, you're going to take money from them, and it's going to cost them. And so if you combine these three concepts, and that's a really key one to understanding how these work and what keeps them secure, is that you'll actually make more money by doing the right thing than the wrong thing. Next up, we have distributed consensus algorithms. We're going to talk about a few of these today, but these are the idea of how do you take this network of hundreds or thousands of nodes or like people running software around the world and get them to agree on one view of the network. And you have to do this while not knowing who those people are. You don't know who they are, they might be trying to attack the network, and you need them to somehow agree. And this was a pretty hard problem for a while until Bitcoin came out and sort of combined these things. Then we have cryptography. These are called cryptocurrencies. It's a big part of it, but it might not be exactly what you think of when you think of cryptography. You might be thinking of encryption, which is where we hide data so nobody else can see it. And the thing about most blockchains is they're actually pretty public. Most of the data is not hidden, and anybody can see it. This is true in Bitcoin and Ethereum. And there's other currencies that are coming out these days that focus on privacy and use encryption heavily. But the major players today, and the majority of them, don't actually really use it at all. So we're going to start off by talking about some of these cryptographic things, because they're really important in understanding what makes the blockchain work. And so we start off with hashing. This is this idea that we can take something like some data, like hello world, we run it through a function, and we get this random looking thing on the outside. This thing, when you run it through it, is always going to be the same size, and it's going to be random. And so if you pass hello world again, you're going to get this output. And so this is a pretty cool way to make something look random, but it's why is this useful to us? And the first reason it has this really cool property that no matter the size of the data, you're going to get the same sized output. So we're talking in bits here, but we say 300 bits, we're going to get 256 afterwards. We can do 3 million bits, we're going to get 256 bits. The idea and how this plays out in blockchains is we can take something like a block, which may be of some size, let's say like a megabyte, and we can take that and get to this 256-bit representation of it. We can do that with a transaction, we can do that with all sorts of things. This is used heavily to identify activity on the blockchain. And the reason why that works as a unique identifier is because if you change anything, you're going to get a totally different output. And so this is in binary here on the left side. This is the only place I have that. But this is all zeros, right? It's 8 zeros. We run it through the function. We get this thing on the right. Now we change one thing. This is the smallest change we can make in computing. We change 1 bit to something different. And this is a completely different number here on the right side. And so this property means that you can't change the history without changing this hash. And blockchains chain these hashes together, which we'll talk about. And this is what keeps the blockchain immutable, and that if you were to change anything, it would change the hash, which would just change everything, and the history would be different. And the last part of hashing is the functions that are used. There's all sorts of types of hash functions. You might have heard of them used in data structures like hash maps. But those are generally not what's called cryptographically secure, which has some extra properties. Like in blockchains, one of the things we want to make sure is you can't actually predict what it's going to be. If I give you a random block, I shouldn't be able to tell you what the hash is going to be without running it. If you could, this would break the system called proof of work, which is one of the consensus algorithms we'll talk about. And then, so these are really important to make sure they work. And if you use a non-cryptographically secure one, you could break the system. Next up, we have this idea of public key cryptography. In sort of the early days of cryptography, you would just take one secret key, and I would have to have it, and somebody else would have to have it. And if I wanted to encrypt data or decrypt it, I would use the same key. The problem with that is how do you share that key with your friend or somebody around the world over the internet without it being secure? If you're over some non-protected channel, how can you do that? And so this is an unsolved problem until this invention of public key cryptography. We call it asymmetric cryptography. This is because you use a different key for encrypting than decrypting. Whereas on the example I just said, we use the same key on both sides. That is symmetric cryptography. So instead of the one key, which would just be like a private key, in symmetric cryptography, you have two. You have a private key, which is a secret that you should never tell to anybody or share or put online. And then you have a public key, which is actually not secret at all. You can share this on the internet. You can post it on billboards. It doesn't matter. There's nothing secret. There's nothing that they can learn about your private key or do anything with this. And why this is important is there's kind of two primary uses of this public key and these public key cryptography systems. The first one is we can hide data. We can use this public key, and anybody can encrypt some data so that only you can see it. And then we can do this other thing, which is called, we can generate signatures, which is very similar to like real-life signatures on some like contract, where if you sign this, everybody can look at that and be ensured that like you signed that contract and it wasn't somebody else. Except the thing with cryptography is that it's almost impossible to forge, and so it's really important. And this is actually what's used for how we actually verify that somebody is able to spend some funds. If I have 1 Bitcoin, the only way I can spend it is by signing a transaction saying, I'm OK to spend that, and that I'm the only one who can generate that. And the kind of high level of how this works, you take some data, you use your private key, you sign it, and you get this thing called a signature. Now you can pass that along to anywhere, like around, and send that along with what data you signed, as well as your public key, and anybody can verify this. So this is how you can generate a transaction securely on your computer or on your system, send it to the network, and everybody can make sure that you did that, but that, and that's how we like authorize who can spend it. And so everybody around the network can make sure that the right people are spending the money. So that was the background of cryptography. That's one of the deeper parts of the talk. We're going to get a little higher level now and talk about like what is a blockchain, because this hashing and signatures are really important for it. So first we start with this block here. And so a block it's just this wrapper. It's a container for all sorts of data. You might have transactions. It'll have a hash. It has some other data. And like it references a previous block. And so this is actually where we get the chain of blocks and the word blockchain from. When we create a second block, we actually include a reference to the previous one. So block 2 has the hash of block 1 in it. And then the third block has the same one. Or it references block 2. And this is where we get the blockchain, because if you remember, with hashing, if you were to change any of the data in block 1, you're going to get a different hash, and now that connection would be broken, and now all these later blocks aren't actually useful anymore and are no longer part of the blockchain. Next up, we're going to talk about how we send a transaction on the blockchain. So we generate a transaction, and then we sign it with our private key. And then once we have that, we have a transaction, but we need other people to see it. So we send it on the internet over to some other node. And these are just software that people run on the network. And so anybody can run a node and just verify a transaction on the network and send it along. And so what happens is the transaction ends up pending on the network. And so it's not confirmed yet. It hasn't been assured that it actually got transferred. And so what the node does is it actually sends it out to all of its peers, to all of its other nodes that it's talking to. And then these kind of continues to create this web where a transaction makes its way around the network. Now, on the network, some of these nodes are what we call like miners. And this one here on the top is a miner. And what they do is they will periodically pick some of these pending transactions and put it into a block and then send that to everybody else. So in this case, this miner picks up that transaction, creates a block, sends it to its peers, and then now that transaction is confirmed, and now your money was transferred to somebody else. And now one of the problems here is we can't just make it easy to create blocks. If it was easy and anybody could create blocks, then there's no time for anybody to agree on the network. Like if everybody was just creating blocks and sending them around, like you can't agree on anything. There's no time. So this is where we get into consensus protocols. In consensus protocols, we have two primary ones that are used today. We have the first one called proof of work, which is the one that Bitcoin uses. And then we have proof of stake, which some other coins use, and is a newer one, but is starting to gain traction, and chains like Ethereum are working on implementing that type of thing. And one of the key components here is that we need to control the rate of how fast blocks are created. If you were able to, like I said, if you create them all the time, then you can't agree on anything. So in some way, in this decentralized world, you need to control how fast they're created so that you can have time for everybody to agree and validate the history. And so with proof of work, the way it does this is by making it expensive to create a block. And they do this with computation. it's just this very simple sort of math problem. It just hashes the block over and over and over again until it gets to the specific hash it's trying to get to. But what's cool about this is why it takes a long time for somebody to create the block. And like Bitcoin sets this to be every 10 minutes, there should be a block. And so on average, every 10 minutes, there'll be a block. But they can send that around, and almost instantly, everybody can verify that that is a legitimate block and that they did the work. And this is where like the proof of work comes in. Now, one of the other things these have to solve for is if two people create blocks that compete with each other. There's two different ones. There's people all around the world creating these blocks. Sometimes they get created at the same time. So it needs to be able to pick which one is the right history. We want one chain, one ledger of the history of these blockchains. So sometimes there's more, and it has to resolve that inconsistency. And so it does this by choosing the chain with what we call the most work. This is effectively an estimate of how much like computation power people put into the chain. And so it makes this choice that if more people are spending money on one part of the chain, that is the correct one. And so that should be the canonical chain. The last one here about proof of work, one of these ideas that it has is this concept called probabilistic finality. Finality means that when you include a transaction and you see that it was put into a block, that you can trust that that won't change in the future. So proof of work doesn't actually have guaranteed finality. So at some point in the future, somebody could come in and change that. Now, I say that, but it is very secure, and it is really hard to change history, especially on chains like Bitcoin that have a lot of miners behind it and backing it up. But it is this idea that it has is that it's not actually guaranteed. It's just kind of in theory. And we're going to go over an example of how this works, of how to like produce a block. But first, there's kind of two other terms I want to define. We have the difficulty, and this is a value that the network configures automatically that says how fast blocks should be created. Like I said, Bitcoin creates this does this so that you create a block every 10 minutes. Other chains pick different numbers. The next one is this thing called the nonce, which is just a random value, and we'll see that used here on the next slide. So here we want to create a block. This block we see here doesn't have a hash yet. We have to create a hash for it. And we have the network difficulty configured to 3. So in Bitcoin, what this means is we actually want to keep hashing the block until we get a hash that has 3 zeros at the front. Like it's really simple, and it's really interesting how it works. But you take this nonce, which is just some value you can change, because if you're creating a block, you've already picked all your transactions and stuff. Those aren't going to be changing anymore. So you just take this nonce and you just change it. And so we start with it at 0. We hash the block, and we get this random thing here. And that doesn't have 3 zeros, so we try again. We just increment it. With the cryptographically secure hash functions, we can't predict what this is going to be. So the only way to get it is just by guessing and checking like a lot. There's so much hashing going on around the world, and it's a lot of energy to do this. And so in the third one, though, we get really lucky. And on the third try, we actually get one with 3 zeros at the front, which means this is now a valid block. And so we can send this around the network. And the reason why miners do this is they're able to include a reward to themselves in the block. They get paid for this. And so they want to send this around the network and do a good job so that they get paid. If they don't, nobody includes the block, and they don't get paid, and they've wasted all this power they've spent creating a block. So, but what if a block gets created at the same time? I mentioned this idea. You have to resolve if 2 blocks are created at the same time, which one is the right one? And so in this example, we start off with the block here, and they all have a height, right? It's this number that goes up over time. And so we start off with one at the 0, and then somebody creates a new block. And so far, this is fine. We have one chain of history, and this block at height 1 references this former one. But then, before another block comes in, we see another one come in. And so now this is a fork in the chain. And so we don't know what the right state is just yet. And so what the network has to do is actually just wait until one of these chains has more work on it. And so what we see here is all of a sudden we see another block, somebody builds on that one, and then I grade this other one out because that block gets removed from the chain, which we call like orphaning a block. And so what that means is that that block no longer gets its reward, none of those transactions are there anymore, and so they need to be re-included on this right side. And so this happens periodically. But like, why does this happen? Like, how come it can't just all create blocks together? Well, the reason is that it's a distributed network where we don't even know who's creating blocks. So some people have different network speeds. They don't see that a new block was already created, so they just keep working on the block they were doing. It takes a while, so once they do it, they want to send it out. Or it's just they may not have seen the new block yet. There's a lot of reasons this could happen, but it is a thing that happens regularly in these networks, and they need to handle it. And so we extend the chain, and now this is the right one. But I mentioned this probabilistic finality concept. While this block is not in the chain anymore, if some miner were to come and start doing work on that side of the chain and producing more blocks, and they made it so it actually surpassed this one on the right, all these ones on the right side would get undone. And these blocks would now be orphaned, and when that sort of happens, when one side of a chain gets sort of undid and the other side was already there, we call it a reorganization or a reorg. And so with proof of work, the kind of main benefits here are that it's pretty simple in its concept. Like it works really well, it's battle tested, it's been used in Bitcoin for 10 years now, and hasn't had any major issues in the Bitcoin system. And so it's a really solid choice if you're building a new blockchain. But some of the problems are it uses a lot of energy. It just hashes nonstop. And so it's a lot of power around the world that's going to just producing these numbers. And so you can argue whether or not that's worth securing the chain, right? You can compare that to how much energy do banks spend and how much energy does this spend. And you can make arguments for it, but if there's options that don't expend as much energy, maybe that's something we should consider. I've talked about probabilistic finalization a lot, but this is potentially a concern. This is why you see exchanges and such with things like they need 6 confirmations, right? When you send it to an exchange, it doesn't instantly show up there, or you can't use it yet. They wait until there's a number of blocks, and this is to hedge against the fact that if there's over some number of them, they expect that it's too expensive for somebody to change that anymore. And then the security is dependent on this decentralized mining force. If everybody's working together, there's all sorts of attacks they can do to change history and attack specific entities. And proof of work sort of pushes miners to be centralized. It does this because if you're buying a lot of hardware to run mining software and you're getting really good deals on electricity, what's going to happen is you get economies of scale and benefits from that. And so you kind of keep doing that and keep getting it all together, but then it reduces the security of the chain. So this is kind of a problem that isn't totally solved. And then lastly, we have slower blocks. Because it takes a while to do this and everybody's doing it at the same time, if we make them too fast, we would always be seeing these reorgs. We would always be seeing these blocks that get undone later. And that's not good for the miners because if they keep not getting their money for all the work, they're not going to be happy. Ethereum did an interesting thing here where they've actually reduced it where they have 15-second block times with proof of work. But instead of not paying for these blocks that get removed, they actually pay them a little bit. So it's not all of it, but it's some of it to at least just kind of handle that. Next up, we have proof of stake. This is a newer idea that's implemented in some newer blockchains. And it's a different model that doesn't rely on repeated hashing and doesn't expend a lot of energy to produce blocks. It's fairly easy to create blocks. The way this is done is that people around the network can put money into the system and sort of lock it up where they can't spend it. And what happens here is that gets them into this pool where they can then, the network will randomly sort of choose somebody to produce a block around the network. So it's not everybody working at once. The network has the ability to decide who should create this block. And so it's asked them to create the block. They do that. It's really easy. There's not all this work they have to do to create it. And then other nodes validate it. And if they created a valid block and didn't do anything malicious, they will get paid for it. And if they cheat, they'll get punished. And the way they get punished in proof of stake is that it just takes some of the money they put up in the system. It's like a security deposit on your rent, right? If you try and mess up something, it's going to cost you. And so this is exactly what proof of stake relies on to keep the chain secure. And so this is that idea of crypto economics coming back. And it's this idea that by creating it so you make more money by doing the right thing and you lose more by doing the wrong thing, you can sort of have security on a chain. And so with proof of stake, it's not as easy to explain as proof of work because there's multiple versions of it. There's no one thing that everybody uses, whereas proof of work, it's very similar in all the different implementations. There's kind of 2 main ones that are used these days. There's delegated proof of stake, which is, we're not going to talk about the details of these, but this is a type of it that the chains like EOS uses, Tezos, and Steam. Tezos is slightly different. They call it something else, but it's close enough. And then out of Ethereum, they're working on this protocol called Casper, which has this one thing called Friendly Finality Gadget, FFG, and another variant called CBC, which is Correct by Construction. And this is being actively worked on. It has been for a while. And they're planning to upgrade this. They're planning to implement this instead of proof of work in the next big Ethereum upgrade. And this one in particular has some interesting properties where they actually structure it in a way to incentivize decentralization. So we can talk about it after this or ask questions, but it's a really interesting model that they've set up there. And so some of the benefits here are that it has faster blocks. Because it's just picking who creates it, you don't have all this competition. You can speed up how quickly you can create blocks. It doesn't waste energy as much. And then the punishments are explicitly defined. Instead of proof of work, where the punishments are sort of based on how cheap your electricity is or how cheap you can get hardware, in proof of stake, it's just this value on the network. If you lock up 5 Ethereum and you do something bad and it's going to take 1, it doesn't matter who you are, it's still going to take 1. And so it tries to be a little more equal around the network. And the main problem with it is that it's just less battle tested. It hasn't been used as long as production systems, especially not the newer ones like Ethereum's working on. And it has different sort of decentralization properties. And so we need to see more of it in the wild to see if it actually plays out. But this is the other major one that chains are using today, and other chains like Ethereum, the major ones, are trying to upgrade to. So with this, we know how blockchains work, and then we go over we go over the consensus, how they agree on this history. But then going one level deep, we have to talk about how money moves in these systems. How do they actually structure their data so that you can transfer money between two different people? And similar here, we have two different models we're going to talk about. The first one is called the UTXO model. This stands for unspent transaction output, and this is what Bitcoin uses, and all sorts of other chains since Monero, Zcash, and Cardano. And so what this means is that a transaction has these inputs into the transaction, and it has outputs. And outputs can be spent or not. If they're spent, they're worth nothing. If they're unspent, they're worth whatever the value is on it. And an interesting thing that comes from this is that there's actually no concept of a balance for an address. This model is very similar to cash in your wallet. So if I want to know how much cash you have in your wallet, you have to take every single bill and sum it all together to get the balance. And so this is exactly how it works in Bitcoin and in the UTXO model. If I want to know how much money an address has on the network, you just sum up all the unspent outputs, and that's your balance. And so to generate a transaction, you start with this empty transaction. And so for this example, we're going to say I want to send 3 Bitcoin from Alice to Bob. And so to start, though, in our wallet, we only have an output that's worth 5 Bitcoin. So how do we send 3? Well, we add an input to the transaction. And so we only have 5, so we add that in, and we say, all right, 5 Bitcoin goes into this transaction. So now we have 5 Bitcoin to work with, and we can send it kind of wherever we choose. And I said we want to send 3 to Bob. So the first thing we do is we define 3 that goes to the destination, which would be Bob here. But then there's kind of 2 left. And so we take one of it, and just like if you were paying at a store for something, you need change back for your $5 bill. And so here we get the one BTC back, and we send that to ourselves. But if you're paying attention, there's only 4 on the right side. So there's 1 Bitcoin that's sort of missing here. And so this is actually the fee of the transaction. In the UTXO model, the fee is not explicit. It's sort of implicit by the difference between these inputs and outputs. The next model is the account model. This is what chains like Ethereum, EOS, Tezos, and Stellar use, and plenty of others. All these are used by way more than I'm listing here. And so this operates a lot closer to a bank account. And you have this balance of an account, and then it just changes over time. It's this mutation over time of a balance changing. It's just like spending your credit card. It's going to deduct a balance and create a transaction. It's not going to create a new account and send it over there. And the way this works is we want to create a transaction. We start off with sort of the state of our system. And so we just have accounts and we have balances. And so in this case, Alice has 5 ETH. We're also going to try and send 3 to Bob here. And so when we specify it in the transaction, it's very explicit. We say this is from Alice to Bob. We send 3 ETH, and we say I want to pay 1 ETH in the fee. And so when that gets executed, we end up with this new state where Alice has 1 left. We didn't have to do anything with change because it just subtracted the 4 ETH from her wallet. So we have 1 ETH left, and then Bob has 3, and the miner has 1. And so those are really basic transactions and how they work. But one of the really cool ideas with blockchains is that they have this programmability aspect of it. They have programmable money, so you can make them do interesting things. So we're going to talk about how Bitcoin and Ethereum do that. We start with Bitcoin script. This is a simple sort of stack-based language. It's not Turing complete, which means it can't do everything. It can only do some things, and then it doesn't have any loops in it. So it's this really basic programming language. The way this works is you have your outputs, and they include a partially complete script. It's actually not runnable on its own. It won't work. And then when you spend it, you include the other half of the script. And then when you smash those together, you get this total script. And when the protocol is trying to decide if you're allowed to spend that money or not, it says that script must evaluate to true. And now because this is dynamic and you can program it to do all sorts of things, the protocol defines these standards for how you send money around. And so there's standards that you can use so that wallets and exchanges and all these sorts of people can implement and accept them. So we're going to talk about this one here called pay to pub key hash. And so what this is actually what happens when you normally send Bitcoin from one person to another. You're sending to their pub key hash. So an address in Bitcoin is actually the hash of your public key. And so what happens here is we have these 2 parts. The top part is what we see in the output, and it's called the script pub key. And then on the script sig on the bottom is what we include in the input. And so We're going to go over an example on the next slide of this. But before we get there, these ops are what's called opcodes. These are just operations you can execute that are predefined. Things like duplicating something or hashing something. And there's all sorts of other ones here. These are just a few that exist. And then these little angle bracket things are where we're going to put in variables. So in this case, if we were going to take that transaction, send from Alice to Bob, this pub key hash here at the top would be Bob's address. And that's how we specify who it goes to. So we're going to walk through how this gets executed in Bitcoin. So we smash those things together where we have at the front this sort of part of the input, this SIG and this pub key, and then we have the rest of it. And then we have the stack on the left, which will be like changing over time. So the first thing that happens is we just have two variables on the stack, so we just push them. There's nothing to do except for put them on the stack. Next up, we have opdup, which just says duplicate the top item. So now instead of one public key, we get two public keys. And then we have hash 160. This is the hash function that Bitcoin uses to produce an address from a public key. And so when we run this, it takes the first item on the stack, this public key, and turns it into an address, which we'll call pub hash A. And now we have the second pub hash that was included when we first created the transaction and sent it to Bob in this case. And so now we pushed that on the stack because it's just a variable. And now we have just two things left. The first one is equal verify. What this does, it says the top two things should be equal. And so in this case, the two hashes should be the same. It should be the same address. And so once that happens, it will work. And if not, it will fail and say that you can't spend this output. And now we just have the signature and the public key left. And we have checksig, which checks the signature for validity and makes sure that it is a valid signature to be able to spend this output. And then we get true. And that's how we spend money on Bitcoin. And so this is just like one example of the most basic case. And there's all sorts of different variants of these and some really cool things that you can do with them. But we won't talk about those today. We'll move on to the Ethereum VM. In Ethereum, they've implemented a Turing-complete virtual machine. This means that you can do arbitrary computation, and effectively, you can compute anything with enough time and resources. These get deployed to the network as these like stateful smart contracts. So you can think of these like when you deploy a contract on Ethereum, it's this singleton that lives in this distributed world that has state that you can change over time. And so you specify all your functions and everything up front, and then it just lives in the system. And then later you can call functions on it and make it change state. The way that this works there is that you can't just allow people to do anything they want because everybody on the network has to run that computation and execute it. And this is so that they can make sure that the right thing happened. Everybody executes it on their own so they get to the same state. And if they don't, then there's some sort of bug, basically. And the way they make this so you can't do just an infinite loop that would just halt the network is they meter the operations. They make sure everything costs a specific amount of what they call gas. And then this is used to prevent DOS attacks where you can't just halt the network. And this is how they limit how much goes in any given block. And it makes it so that complex computations cost more. So it sort of incentivizes you to do cheap things on the chain, because if you do expensive things, it's going to cost you a lot more to do it, and all your users who are trying to interact with that part of the system. And then what's really cool about this is they've implemented all these higher level languages on top of it that look a lot like languages we're familiar with and use today. Two of these are one of these is Solidity, another one that's a newer one is called Viper. And so the way this looks is like this. This is the Solidity language, and this is the interface for what I'm calling a partial ERC20. If you've heard of ERC20, it's the token standard that people use on Ethereum to have these custom tokens you can send around. And this is part of what that interface looks like. It looks very familiar if you've done much programming. It looks a lot like JavaScript or some other languages. And so we have a function that you say, what is the balance of some address? And it returns an integer. And then the same thing, if you want to transfer to somebody else, you just say, all right, I'm going to transfer to this address and this much. And then it tells you if it's succeeded or not. And then here's an actual implementation of that interface, or part of it. We have a contract, and then what we do is at the top, we have this thing called a mapping. This is a hash map. So the way tokens actually store their state on Ethereum is just a hash map of an address to a balance. And so we just have a variable here that lives just on the network, and anybody can read that and kind of see what's happening. And then we have the transfer function. And this is how we move funds from one person to another. When somebody calls transfer, they pass in who they want to transfer to and how much. And then it's a really simple operation. We just deduct how much they're sending from the sender, which is now who it's from. And then we just add that to the other person, and then we return. In practice, they're slightly more complicated than this, but this is how they work. They're actually really simple, and they're not that complicated. And there's a lot more in blockchains. This only scratches the surface. There's a lot of really cool ideas like layer 2 or privacy coins, and ZK snarks, and all sorts of really cool stuff. And it's this like space that has so much new stuff, and a lot of new ideas are coming out of it, and it's really only getting started. So I hope you'll like read more about this and learn more. And yeah, that's it for me. Thank you.
Awesome. Good job.
I don't know.
Awesome. Well, thank you all for joining us here today. It's been exciting, and we hope you've had a chance to sort of see the promise, see what we've seen play out, but really understand the heart of the technology. When I started, Ethereum didn't exist. Half of what Jake talked about wasn't there. That was 4 years ago. Imagining what's going to happen in the next 4 years is incredible and exciting, and a chance to pioneer that has been amazing. We want to thank all of you for joining us here today. We have hors d'oeuvres and drinks after questions and answers. But just to let you know, in case you wanted to head out to the bathroom, please do come back. Hang out with us. Anybody with a Coinbase shirt is here to talk to you. But let's hit some questions and see what people have to ask.
And so just to let you guys know what we're doing for questions is we're using Slido. So you can just go to slido.com, search by the hashtag startup, and then you can enter your questions and they will automatically pop up on the screen, and you can also upvote questions as well. So that way everyone can see what questions are being asked. And then I can actually answer 2 of these questions for you guys. Will these slides be made available, and will a recording of this presentation be posted? So all talks from Startup Central will be available on YouTube within 48 hours. So check the AWS YouTube channel, and you will be able to find both this presentation and all the presentations from this area. Let's see. Okay. Are there any plans to or work to standardize asset codes across cryptocurrency space like the Fiat ISO 4217 standard?
I can answer? Sure. I don't know. I don't know what that standard is, but I assume you're talking about like tickers of asset codes, like ETC or BTC and stuff. That's what I'm assuming here. As far as I know, no. And this is actually something we've had to deal with recently of adding assets. It's like, all right, what do we need to support for the tickers? What does our UI need to support? And it would actually be really cool to see more standardization so we can make the right choices there instead of just kind of picking something.
Yeah, that's been interesting for me as well, because part of the incredible opportunity in decentralization can also be part of the challenge, because you want to bring everybody together. You need to create consensus in order to have a decision. Actually, we were at DevCon and got a chance to talk to a lot of people. The standards are like far-reaching, and there's a lot of conversation about that. So I think it's evident, but not that we're aware of specifically.
When is XRP going to be listed?
Great question. Can't answer it. But do encourage you to follow us on Twitter, at our blog. All of the announcements go out there, and that's the best way to find out about any of the future listings.
So POW and POS are good ideas. However, human greed will undermine a truly decentralized authority. That's proof of authority seems to be the answer. What are your thoughts?
I'll take first stab at the question, and then Jake can take it on. Yeah. So at a high level, the sort of brief of it is this is another type of governance mechanism, and it's been exciting. Some of my friends are working on it, and I think that is incredible. The more governance opportunities we have, the more diversification and the more opportunity for consumers to choose which governance they want. So I think, like Jake mentioned, a lot of these have pros, a lot of these have cons, and proof of authority is likely to be there. I also think human greed is true. What a shame. It's hard.
Yeah, I mean, for me, human greed is a big part of this, and proof of work and proof of stake both have like fairly centralizing elements. Proof of stake has this idea of like cartels, of like somebody who has all the money sort of controls the system. Proof of work is similar, of like miners doing that. But I don't know if proof of authority is the answer, because you're making it explicitly centralized, and in some cases that's a good choice. And there's a lot of ideas in blockchain that are really useful even in a non-decentralized way. But proof of authority of like a public decentralized blockchain is, I think, unlikely the right solution. But I'd be happy to talk more about it.
Jake's a good one to get a good argument on the different types of consensus mechanisms out there. And I'll add on the different things. We at Coinbase, we don't think that there will be one single solution to everybody's problems. I don't think that's ever been true in the history of the world. So what's really exciting is that you can have all of these different things and utilize it for different solutions. So proof of authority might work for one thing, where proof of work works better for another thing. Bitcoin has historically been a very good store of value, highly secure, whereas Ethereum's been focused on Turing complete and how do you have all of these other opportunities. And I think we'll continue to see that grow because the iteration and the experimentation is exploding in this industry.
Well, this is an easy one. Do you have a blog where you share your knowledge on cryptocurrencies and blockchain?
Not yet. Jake has a Twitter.
Coinbase
is the exact right place to go.
Coinbase has an engineering blog where we share some of these ideas. We had a blog post about some of the work we did, our team did fairly recently on Bitcoin where we basically made the system operate better by implementing some more advanced features in our systems to have better reliability of our systems and exchanging Bitcoin on Coinbase.
And I think it's engineering.coinbase.com or engineering.blog.coinbase.com. Just Google Coinbase Engineering Blog and you will find that. And we put all of our work out there, what we found in the industry, what's working, what's not.
Next, is it truly decentralized, seeing that there are a few enterprises running huge mining operations?
Yeah, that's a great question. I don't know. I think the idea of decentralization is still here with us. I think the way it played out was incredibly interesting with miners and proof of work, and that's why you saw these new chains come out. And that competition, that opportunity for consumers to choose where they wanted to be, well, that's up to you. Is that too centralized for you? That's fine. Go choose a blockchain that doesn't have that governance protocol.
Yeah, I mean, there's a lot of ideas in this space for how to change this, but I think it depends on the chain, right? Certain chains are more decentralized than others, especially in the proof of work model. Bitcoin has a lot of different miners. There's a few of them that control a lot of it, but at least it's not majority control. You take this example with some other smaller chains, chains like Bitcoin Cash or the latest chain, Bitcoin, like Satoshi's Vision, SV. And so these ones have much different properties of decentralization because they have more centralized mining behind them. Bitcoin SV has 2 major majority miners on the network right now. And so you could argue it's not as decentralized as other ones. And I think that's its own sort of problem that I think a lot of people are trying to figure out is, in practice it's played out that it does get centralized because of economies of scale, because of the people with the money are able to invest in these exploratory sort of technologies. And it's sort of an unsolved problem, but I think it can be, and there's a lot of people working on a lot of really cool ideas of how to improve that story.
Yep. And we'll get a spectrum no matter what. Some things centralization is the right thing for, some it's not. We'll see.
Here, I'm going to flag this one for you guys. Are you hiring?
We are hiring. Definitely join us for our drinks, for our hors d'oeuvres, because we're happy to talk to you about that. We're hiring, we're excited.
Yeah,
we want you to join us.
Everything, so.
Come see the frontier of this space.
How can blockchain be used to secure apps in a zero-trust architected environment? Can we use MBC for integrity and identity of app transactions?
Ooh. Yes. Anything?
I don't know what NBC is. So
I think
I'm not sure
the network, the NBC network. The TV network?
The TV network?
Are we talking? Oh, BTC? Oh, yeah, okay, it was a mistype. It's cool. Can we use BTC for integrity and identity of app transactions?
Yeah, definitely. This is where hashing comes into play. This is actually, Amazon's new, quantum ledger DB is effectively sort of a blockchain. If you read about it, you'll notice a lot of things I talked about. It's just history that hashes everything together. So if you change the hashes, it breaks it. And so people use Bitcoin like this too. One of the opcodes is this code called op return, which is you can just put data. If you hear about people storing images or stories or whatever on the blockchain, they're using this code where you can just store data. And so one of the things you can do is prove that something was in some state at some point in time by publishing its hash to the blockchain, where you can say this document existed a week ago because I published the hash of it there. And because you should not be able to produce any sort of content that produces the hash without just knowing what it was. That's a way to sort of verify even things off blockchain, and you can sort of settle it onto the chain. That's used a lot in layer 2 stuff as well, which I didn't get to talk about, but it's one of these scaling ideas they have of building secondary layers on top of something like Bitcoin or Ethereum or these other base layer chains. And then they can build things that are faster, but eventually they kind of publish things there for sort of using its security as a central source of trust.
Let's see. Can you provide some more use cases for blockchain outside of payments, trading, or currency?
Definitely. Those are obviously the main opportunities and the ones that we've seen to date. But people have talked about identity on the blockchain. It's secure. You can move it around. It's cross-border. What does that look like? What does that world look like when you could put your identity on it? People have investigated healthcare records on the blockchain, and these all have lots of things to be figured out, implications that need to be resolved by people. Brave browser is another great example of that. So you can do micropayments in this technology because the fees are lower, and there's lots of opportunities. Do you have any favorites, Jake?
Nope. Nope. I think, yeah, they're pretty cool. They enable a lot of different things, and cryptography is this really interesting thing that like something so simple as just like taking some value and turning it into this random thing has so many implications and so many uses. So like I don't even know if we know them all yet.
Yeah, I think there's a lot of interesting things being worked on. Actually, Andreessen Horowitz has a great blog about, I think it's called Crypto Canon, what's going on, what's new, what's being worked on. And just like the internet, it's going to be far-reaching. Many things we can't even fully understand what they would look like, but definitely take a look at Crypto Canon specifically, and just think about any time you want to move value instantaneously anywhere in the world. You could put your title of your house on the blockchain. You want to move value securely and instantly, so it has the reach of the internet in no time.
Okay, so I can see that there are still a lot more questions that you guys are adding, but I'm going to make this, we're going to pick one more public question, because then we are going to start setting up for the happy hour that is immediately starting after, and Jake and Kristen will be around to answer questions, as will the rest of the Coinbase team. So I'm going to do one more question here, and then feel free to approach them with your questions after the session. And let's do, as crypto becomes more popular and issues such as custody, volatility, liquidity come up, what do you think is the one thing holding back mass market adoption?
Oh, I love this question. I've thought a lot about this. So what's fascinating is that as a society, specifically in America, our identity is really close, our national identity is really closely tied to the idea of our national currency. And so we, as individuals and through generations of time, really have to expand our mind and our understanding of what it looks like. What does currency look like? What can programmable money do? And some of that just comes through useful applications. We don't all know how like the internet works and all the depth of that, but we still use it because it gives us value. So I think mass market adoption, we need to have something that provides us value. And that'll help us to separate the idea and the stories we've told ourselves about how money works and what that looks like and the limitations of it, and we can really get beyond into a decentralized world.
Yeah, I have two answers for this. One is like stability, which means I think a lot of different things. The prices aren't stable, which makes it pretty difficult to like try and use this thing and know what it's going to be worth tomorrow. That's its own sort of problem. But even outside of that, like one of the reasons that the community is not necessarily stable, there's a lot of tension, a lot of different competing camps and competing blockchains that are trying to like be the one true currency or be their own. There's just a lot of like volatility in the space because of that also like helps the price not be stable. And so that's like outside of investment or expecting it to go up or something. It's unclear. Like it's not good to pay your friend if like they're going to lose half the money tomorrow. It's not that great. The other side is like just user experience. It's really hard to use these things. Like I talked a lot about the details. Like you don't need to know these details to use this, but at least because of like the tech that exists today and because of the like services and wallets and stuff that exist, like a lot of this stuff gets shown to you, and you have to sort of know about these things, and you shouldn't, right? I don't know how my credit card works, but I use it and it works fine and it does what I need it to do. And so blockchain should, at least in the case of like payments, do very similar things. Like it's why, like Kristen mentioned a part of her talk, like why would you use the blockchain when you have a credit card and you actually get paid rewards for it and stuff? And there are things like proof of stake and stuff that try and get like, even without doing anything, you can like get money or gain interest and stuff. And there's some cool things like that in the space as well.
And that's actually also where Coinbase is a great option. It's easy to use. You sign up with an email, same way you would a Facebook or a Google, a Gmail account. Really simple. So if you want to test it out, if you haven't had a chance to do that yet, just go to coinbase.com, grab some cryptocurrency, and it's the best way to learn, to get involved, and to start understanding it. And then come build the frontier with us, come build all the new use cases and see what it's going to become. Help us make that mass market adoption.
Okay, so as mentioned, we have to cut off the public questions at this moment, but we are going to be, but Jake and Kristen and the rest of the Coinbase team are going to be here for the next hour, so feel free to approach any of them with questions. And I want to thank you guys for coming to speak today, and you guys for all coming out. Thank you very much.
Thank you. I will add, we started by having you talk to your neighbor. So if your neighbor's still here, find out if their perspective has changed a little bit and if maybe they've learned something new from this talk. Thank you all.